Imagine a wall. Not a wall built on solid earth, but a massive barrier stretching 33.9 kilometers across the open, unforgiving sea. Now, imagine trying to build this wall while the ocean itself fights back, throwing 6-meter tides at you twice every single day. We are talking about a current so violently powerful as it squeezes through construction gaps, that it can rip 10-ton boulders straight off the seabed and roll them downstream as easily as if they were loose gravel. Common sense would say this is impossible. The ocean does not want a wall here. But South Korea built it anyway. In 1991, the South Korean government stood before the world and announced the largest, most ambitious maritime construction project in the nation's entire history. The vision was staggering. They would construct a continuous, unbroken wall from the port city of Gunsan all the way to the headland of Byeonsan. This would require linking 4 massive dike sections across 3 separate island chains and blocking 2 major river estuaries. Once completed, this mammoth structure would completely close off 401 square kilometers of the Yellow Sea. To put that into perspective, that is a body of water 2/3 the size of Seoul. It is 5 times the size of Manhattan. Behind this relentless wall, the untamed sea would be forced to become a placid lake. Over time, that lake would be drained and filled to become solid land. And eventually, that new land would become a sprawling, futuristic city. $20 billion, 19 grueling years of construction, the promise of 700,000 future residents living, working, and driving on ground that, today, is literally the ocean floor. But drawing a line on a map is one thing. Actually building a mountain underwater is something else entirely. Now, watch exactly what it takes to build a megastructure in water that absolutely refuses to be tamed. Engineers who have spent their entire lives mastering infrastructure are usually prepared for the worst.
The sea demands respect. I've seen worse storms, but you can never afford to be complacent on this platform.
The very first, almost insurmountable problem the builders faced was the seabed itself. The southwest coast of the Korean peninsula is not made of solid, dependable bedrock. It is tidal mud. It is soft, heavily saturated, highly unstable sediment that has been patiently deposited over thousands of years by the Mangyong and Dongjin rivers. If you were to stand out there at low tide, this mud stretches out flat and grey, all the way to the horizon. It is a desolate landscape, soft enough to quietly swallow a grown man right up to his waist in seconds. But at high tide, the situation transforms. 6 meters of dark brown seawater rushes in to cover the mudflats completely. There is nothing visible, there is nothing solid to anchor to. You simply cannot place a heavy wall on tidal mud. If you try, the sediment instantly liquefies under the immense load. The structure begins to tilt, and before you can even lay down the next layer of stone, the relentless pull of the tide tears the tilted, compromised section apart. This seabed does not support weight. It swallows it. So, the engineers had to do the unthinkable. They had to strip the ocean floor down to the stable clay hidden deep underneath. They brought in cutter suction dredgers. These are not just boats. They are floating factories, equipped with terrifying, rotating cutter heads the size of cars. Anchored offshore in the churning water, these mechanical beasts ground the soft mud into a thick slurry. This slurry was then aggressively pumped through floating pipelines, hundreds of meters of thick steel pipe chained together on bobbing pontoons, transporting the waste to disposal areas miles behind the construction zone. These monstrous machines worked 24 hours a day, 7 days a week, without pause. A single dredger was responsible for removing millions of cubic meters of material every single month. The noise they made was deafening, carrying for kilometers across the water. It was a low, guttural, grinding roar that never stopped, day or night. It was the literal sound of the seabed being eaten alive. They had to dig a foundation trench deep enough to reach competent, hard clay beneath the treacherous tidal sediment. In some agonizing sections of the route, that stable layer was 20 meters down. Imagine that. 20 meters of unstable, shifting muck had to be violently scraped away before a single, solitary foundation stone could be placed. But the ocean is not a passive canvas. The trench refused to stay open. Every 6 hours, like clockwork, the current reversed. As it did, it dragged fresh sediment right back into the pristine, newly cleaned trench, covering the desperately needed clay with a thick blanket of fresh mud. This created a terrifying race against time. If the engineers could not place the gravel foundation before the next tidal cycle buried the clay, all of that massive dredging effort had to be repeated. From absolute zero, the crews were forced to operate on razor-thin tidal windows. 4 times a day, the furious current drops to near zero for roughly 30 precious minutes. This is called slack water. During these fleeting moments of calm, specialized split-hull barges, each heavily loaded with 3,000 tons of crushed rock, would maneuver into precise position over the trench. The tension on the water was palpable. Their massive steel hulls would literally begin splitting open at the seams just as the current died down. With one violent, explosive release, the barge would dump its entire 3,000-ton cargo into the depths. The barge empties in mere seconds. The moment it does, it desperately guns its engines and pulls out before the current wakes up. If a captain missed this window by even a few minutes, the returning current would hit the broadside of the barge with the force of a freight train. A fully loaded, split-hull barge caught in a 5-knot tidal stream cannot be steered. It cannot be stopped. It is at the absolute mercy of the ocean. This exact nightmare scenario played out in 1998. A slight timing error left 2 barges trapped in the channel when the tide viciously turned. They collided. One was violently pushed until it grounded hard on the mud flat, heeling over helplessly until the next tide finally lifted it free. The other barge had its massive anchor chain snapped like a brittle twig. It drifted blindly into the active construction zone, crashing heavily into a critical piling. But laying the rock is only half the battle. This gravel bed is the ultimate foundation for everything that will sit above it. Every single stone must settle within strict millimeter tolerances on the exposed clay. The massive dyke that will eventually rise above this bed weighs hundreds of thousands of tons per linear kilometer. If the gravel bed is uneven by just a few centimeters, the dyke will develop differential settlement. Microscopic cracks will form deep within the structure. High-pressure seawater will inevitably find these cracks and enter. The cracks will widen. And eventually, the mighty dyke will fail from the inside out, completely invisibly, while 401 square kilometers of trapped sea waits menacingly behind it. To prevent this catastrophic failure, survey vessels continuously crossed and recrossed the trench in tight grid patterns, using advanced echo sounders to map the gravel surface down to centimeter accuracy. If the computers detected that a section of the foundation was too high, human hands had to fix it. Professional divers would descend into the freezing, crushing depths to the trench floor, in a maximum of 6 meters of murky visibility, in water so aggressively cold that their fingers would literally stop responding. After 40 minutes, they went to work. They took heavy rakes and leveled the stones flat, by hand. They leveled the foundation of the longest seawall on planet Earth with their own frozen fingers. This is a detail most people completely miss when looking at a mega project. Before the steel, before the concrete, there are just divers on their knees, submerged in dark brown water, desperately pushing sharp gravel with their freezing hands. That is how a miracle begins. With the foundation finally secure, the dyke itself could begin to rise. But understand this. This is not a solid concrete wall. It is an earth embankment, constructed in the middle of the open sea. If you look at its cross-section on a blueprint, it does not look like a wall. It looks like an entire mountain resting on the seabed. At its absolute widest, the base of this structure stretches 535 meters across. That is wider than 5 full-size football fields placed end to end. The average width is 290 meters. The average height from the ocean floor is 36 meters, topping out at a staggering maximum of 54 meters. You are looking at a 17-story building built entirely underwater, stretching 33.9 kilometers from shore to shore. When you visit today, only 11 meters of this colossal structure show above the waterline. The other 25 to 40 meters are hidden below the dark waves. You can drive your car across it right now on a perfectly paved, 2-lane highway at 80 kilometers per hour, looking at the breathtaking ocean on both sides with absolutely no idea that you are driving on top of a structure taller than most of the apartment buildings in the city you just left behind. But how do you build an underwater mountain? The secret lies in the core. The core of this megastructure is sand. Millions upon millions of cubic meters of dredged sea sand. But you can't just dump sand into the ocean. It would immediately wash away. Instead, they pumped this wet sand slurry through floating pipelines directly into the rising structure, building it up painstakingly, layer by layer. To hold this massive mountain of wet sand in place while it settled, engineers utilized a revolutionary technology, geotextile tubes. Imagine giant, temporary retaining walls made not of steel or concrete, but of fabric. These were massive, specialized fabric cylinders, each 30 to 50 meters long. They were laid out on the ocean floor and pumped full of sand slurry on site. As they filled, they inflated from flat strips of heavy cloth into incredibly solid sausages, 2 meters in diameter and as hard as rock. These massive fabric tubes were stacked in endless, uniform rows to hold the fragile sand core tight while the water drained out and the sand consolidated into a solid mass. Across the entire project, engineers deployed 26 kilometers of these geotextile tubes. By replacing traditional, painstakingly slow rockfill retaining walls with these massive fabric sausages, the project saved $6.2 million and shaved 7 critical months off the timeline. But just like everything else out here, the ocean made this a nightmare. Each and every fabric tube had to be laid, filled, pressurized, and pinned down before the relentless tide returned to cover the work zone. If a tube was not fully pressurized in time, the rising tide would violently collapse the loose fabric. Without that barrier, the fragile sand core sitting behind it would instantly slump, washing away into the dark sea. To protect this vulnerable sand core, the engineers had to build heavy armor. On the seaward face, the side taking the daily beating of the open ocean, they constructed a gently sloped embankment of loose, heavy rock known as riprap. This wasn't dumped randomly. Every single massive stone was carefully placed by a crane operator, ensuring it perfectly interlocked with its neighboring stones. This gentle, rocky slope is a brilliant feat of physics. It absorbs explosive wave energy by allowing the surging water to rush up through the countless gaps between the stones, dispersing its power and then gently draining back into the sea without displacing anything. But it is a fragile balance. If just one single stone washes out of the matrix, the cavity it leaves behind undermines the stone sitting right above it. Then that stone falls out. Then the next one follows. A catastrophic failure of the entire sea face can start with just one misplaced stone. On the inner face of the wall, they used heavily compacted fill, covered with a thick, impermeable clay cap. This clay was crucial to prevent heavy rainwater from seeping down and softening the internal sand core from above. And finally, on the very top, they paved a flawless, 2-lane highway running the full 33.9 kilometers. If you stand on the shore at night and look out, you can see the headlights of cars moving silently across the surface of the dark yellow sea, looking exactly like a road that simply should not exist in the natural world. But here is the most terrifying part of maritime engineering. None of this incredible progress matters until the wall is completely closed. The Saemangeum dyke was systematically built in 4 distinct sections hopping from island to island, headland to headland. Each section was built starting from the edges, slowly growing toward the center. As long as these massive gaps remained open, the ocean tide could flow freely through them twice a day. The estuary could still breathe. The exact moment a gap is finally closed, the water flowing through it stops completely. But the total volume of tidal water trying to enter the estuary does not magically decrease. The ocean still wants to push the same 401 square kilometers of water in and out twice a day. Now, however, it has to squeeze all of that unimaginable volume through whatever gaps are left. Less opening area, same massive volume of water, equals a violently faster current. Watch what happens next, because this is the exact moment where this $20 billion mega project almost died. As the construction sections grew longer and the final gaps shrank narrower, the tidal volume stayed brutally constant. By the final stages of closure, the current ripping through the remaining gaps exceeded 6 meters per second during spring tides. That is 21 kilometers per hour of solid, heavy seawater tearing through a channel that is intentionally being shrunk every single day. At a speed of 6 meters per second, standard construction materials become useless. Loose rock, no matter how heavy, does not sink to the bottom. It tumbles downstream like pebbles in a stream and disappears into the abyss. The engineers tried gabion baskets, heavy-duty wire cages, aggressively packed with jagged rock. The unbelievable force of the water simply ripped the wire open, turning the rocks into lethal underwater projectiles. The math became a matter of life or death for the project. If one gap was closed before the others were completely ready, the final remaining gaps would be forced to carry the absolute full load of the ocean's fury. If only one gap was left open, the current would accelerate to a speed that becomes physically unconstructible. No rock heavy enough exists, no steel cage strong enough holds. To succeed, both of the massive southern gaps had to be closed at the exact same time. Zero exceptions, zero margin for human error. They needed a test run. June 10, 2003, the day the northern gap was scheduled to die. To beat the ferocious current, they used a technique called combined vertical and horizontal closure. Instead of trying to block the gap slowly from one side to the other, which would just speed up the water, they decided to raise the entire seabed across the full width of the opening simultaneously. By doing this, the gap does not just get narrower, it gets shallower. Less depth over a massive, wide sill means less concentrated hydraulic force. It gave the heavy rocks a fighting chance to actually stay where they were dropped. Hundreds of massive dump trucks lined up bumper to bumper along the newly built dyke crest. They waited in absolute, tense silence for slack water, that tiny 30-minute pause between the raging tides. When the signal hit, every single truck dumped its load at the exact same time. A deafening avalanche of rock, gravel, and thousands of specialized gabion bags hit the water. These gabion bags were the ultimate breakthrough. They were heavy-duty wire mesh sacks, meticulously filled with a precise mix of large rocks and smaller, interlocking stones, with each bag weighing several tons. Unlike loose boulders that would catch the current and roll away, these bags worked as a team. The mesh kept the fill together, even when the 6-meter-per-second current slammed into them. When they hit the seabed, they didn't just sit there. They deformed under the immense weight and locked against the bags next to them. Where a massive, loose boulder would be swept away into the dark, a gabion bag, dropped just 3 meters away, would stubbornly hold its ground. Where a heavy concrete block would eventually shift and tumble, the bag right beside it would absorb the kinetic load and stay put. A thin layer of wire mesh became the only difference between an engineering triumph and a $20 billion underwater ruin. The underwater sill rose agonizingly slowly. Centimeters per tidal cycle. Every single cycle was a brutal war. Dump thousands of tons on the slack tide. Wait anxiously. Watch the raging current return. Watch helplessly as some loose stones roll and disappear. Watch as some of the massive bags shift and groan under the pressure, but pray that just enough holds. Measure it. 1 centimeter higher than it was 6 hours ago. Wait for the next slack tide. Dump again. Gain 1 more centimeter. As one exhausted engineer described the final push, rock by rock, tide by tide. It wasn't a dramatic explosion. It was just relentless, exhausting grinding. Eventually, the northern gap closed, and the moment it did, the nightmare shifted south. The water that used to flow comfortably through 3 massive openings was now violently squeezing through just 2. It was time for the final battle. April 21st, 2006. The day the sea finally loses. There were 2 massive construction fronts facing off against 2 raging gaps. Each gap was 2.7 kilometers wide. Both had to be closed on the exact same day. The stakes were astronomical. If one front moved slightly faster and closed first, the entire tidal volume of 401 square kilometers would rush through a single remaining opening. The current in that final gap would instantly exceed any constructible resistance on Earth. The project would fail, violently and publicly. The massive operation started before dawn. Convoys of heavy dump trucks stretched back for miles along both sides of the dike crests. Armadas of bulldozers idled ominously at the absolute edge of the drop. Enormous mobile cranes sat on floating barges directly in the treacherous channels. Teams of engineers frantically zipped around on small survey boats, measuring the current speed in real time, constantly radioing micro-adjustments back to the fleet. The tide began to drop. The computers read 5 meters per second, then 4, then 3. The critical slack window was approaching. The command signal went out to both fronts at the exact same second. It was controlled chaos. Hundreds of trucks dumped simultaneously. A massive cascade of rock poured over the edge into the churning, muddy water. Thousands of heavy gabion bags tumbled after them. Bulldozers aggressively pushed massive piles of staging material directly off the crest. Barges moved in, and massive cranes began lowering 5-ton solid concrete blocks on thick steel cables directly into the violent flow. The water absolutely erupted. The current fought back with everything it had. It grabbed the falling material and desperately tried to drag it through to the other side. Individual rocks tumbled and vanished, but the mesh bags held. They sank, they settled, they deformed and locked tightly against the muddy seabed and against each other. The sill began to rise. Then the tide turned. The current violently reversed direction. Now, both critical gaps were under attack from the inside out. Material that had just successfully settled on the seaward face was now being relentlessly pushed from behind. The gabion bags absorbed the massive kinetic reversal. They groaned, but the sill held. The next slack tide came. More trucks, more massive bags. The sill rose again. By the time evening fell, the water depth flowing over both underwater sills had decreased so much that the tidal current lost its power. It could no longer move the size of the stones being dropped. The mathematical point of critical velocity threshold had been crossed. Finally, everything that was dropped into the ocean stayed exactly where it landed. Over the following exhausting days, the crews methodically raised both rock sills completely above the high tide line. The water finally stopped flowing. For the first time in the recorded geological history of planet Earth, the Saemangeum estuary was completely physically separated from the ocean. The mighty tidal current officially dropped to zero. But while the wall was mathematically closed, it was nowhere near finished. And nature had one final weapon. Vicious typhoons hit the western coast of the Korean peninsula every single summer. These massive storms bring surges that can easily raise the ocean water level by 3 full meters in a single hour. If a major typhoon were to strike the dike before the heavy riprap armor was fully placed and locked, the monstrous waves would tear the exposed, fragile sand core completely apart. In minutes, the sand would liquefy, the core would violently collapse, and the 401 square kilometers of trapped water sitting behind it would explode back through the breach in a tidal wave of destruction. The heavy riprap had to go on perfectly, stone by agonizing stone. Each massive boulder was meticulously lowered by a crane and fitted flawlessly into the interlocking slope. The mathematical angle of the wall was exactly 1:3. If they built it any steeper, the massive stones would eventually slide down under their own immense weight loading. If they built it any shallower, typhoon waves would easily overtop the crest and viciously attack the vulnerable inner face of the wall. To manage the trapped water inside, two colossal sluice gate systems, named Sinsay and Garyu, were painstakingly installed in the southern section. These are massive, fortress-like steel structures designed to precisely control the water exchange between the enclosed, dying estuary and the open sea. When the gates open, seawater cautiously enters. When they close, fresh water flowing from the Mangyong and Dongjin rivers accumulates quietly inside. It is a delicate, terrifying balancing act. If both of these critical systems were to somehow fail simultaneously during a massive storm surge, the water level inside the wall would rise uncontrollably. The dike is structurally designed to withstand immense pressure from one side only. Simultaneous, crushing pressure from both sides would vastly exceed its structural capacity. The internal sand core would instantly liquefy from within. The longest seawall on Earth would simply cease to exist. These gates have to work perfectly, every single time, in every single storm, forever. April 27, 2010, the Saemangeum Seawall opens officially to the world. 19 long years after the first shovel hit the dirt, 2 full decades of brutal construction out in the middle of the open sea. Then, President Lee Myung-bak proudly stood upon it and called it the Great Wall on the Sea. Guinness World Records officially certified it as the longest man-made seawall on planet Earth, 33.9 kilometers long. It beat the legendary Dutch Afsluitdijk, which had held the global record for 78 years, by a massive 500 meters. It is 290 meters wide. It is 54 meters tall at its deepest trench. 2/3 of its immense bulk remains completely invisible, hiding silently beneath the surface. It successfully enclosed 401 square kilometers of territory. It cost $2.6 billion just for the wall itself. The full, sprawling development, including massive land reclamation, brand new infrastructure, sprawling industrial zones, and a futuristic city planned to house 700,000 residents by the year 2050, will cost over $20 billion. This project survived 2 massive Supreme Court challenges. It survived 3 sprawling environmental lawsuits. It was forcibly shut down by court order twice. It survived a complete change of national government. And despite all of that, it still went up. Behind the immense wall today, the radical transformation has already begun. Fleets of earthmovers are building rectangular polder dikes inside the newly enclosed area. Massive industrial pumps are continuously removing the trapped seawater. Specialized dredgers are rapidly filling the newly drained space with millions of tons of fresh sand. They are actively planting aggressive grass to pull the remaining moisture out of the new surface and harden it. What was once soft tidal mud is slowly becoming dry soil. That soil is becoming a solid foundation, and that foundation is rapidly becoming paved roads, buried utilities, and sprawling factory floors. Modern city streets are appearing exactly where schools of fish swam for millennia. Traffic lights now stand exactly where the violent ocean tide used to turn. As of today, the internal reclamation is 28% complete. The massive Hyundai Motor Group has already signed a $6.1 billion investment deal to build a state-of-the-art AI data center and an autonomous vehicle testing complex right on this reclaimed land. They are building the future on ground that was, within our own living memory, the dark bottom of the ocean. But this incredible wall carries a very dark, very heavy cost, and it is a cost that no financial budget line will ever truly cover. Before the wall, the Saemangeum estuary was one of the single most important tidal flat ecosystems in all of East Asia. It was 400 square kilometers of incredibly rich, biodiverse mudflats. Every single year, this ecosystem supported between 300,000 and 570,000 migratory shorebirds. It was the critical, life-saving refueling stop on the massive East Asian Australasian flyway. This is the legendary migration route, stretching from the frozen breeding grounds up in Siberia and Alaska, all the way down to the warm wintering grounds in Australia and New Zealand. These are tiny birds that fly 10,000 kilometers without ever stopping. To survive that impossible journey, they need exactly one place to land, rest, and eat. For hundreds of thousands of years, Saemangeum was that place. When the northern and southern gaps finally closed in 2006, the tidal flats instantly died. The powerful tide that brought the nutrients completely stopped. The rich mud baked and dried. The billions of tiny invertebrates that lived in the wet sediment perished almost overnight. The entire food supply simply vanished. The immediate ecological crash was staggering. Shorebird populations at Saemangeum plummeted by 95% during their northward migration and 97% during their southward journey. The majestic great knot bird saw its population decline by 93%. The red knot crashed by 97%. The incredibly rare spoonbill sandpiper, a species with fewer than 500 individuals left anywhere on Earth, completely lost one of its absolute last viable refueling sites. Scientists desperately tracked the birds with satellites, hoping they would just fly somewhere else. But the harsh reality was clear. Most species had absolutely no alternative staging site. There was literally nowhere else on their entire 10,000-kilometer route with enough food to sustain them. They did not just seamlessly relocate to another beach, they dropped out of the sky. They disappeared. One single wall, 300,000 birds gone, and the devastating human cost was just as absolute. The local fishers lost their entire way of life, too. For generations, between 20 and 30,000 people had worked the rich waters of the Saemangeum estuary. They tended massive shellfish beds, protected vital fish spawning grounds, and cultivated vast seaweed farms. All of it was gone the exact day the tide stopped flowing. The government offered financial compensation, of course, but it was not enough. Money is never enough when the very sea you have fished your entire life suddenly becomes a dry, dusty construction site. For them, this was not an engineering triumph. It was a cold transaction, land traded for the sea, a concrete city traded for a living estuary, the promise of future economy traded for the complete destruction of local ecology. Today, the wall stands proud and unmoving. The new futuristic city slowly rises behind it. The ancient mud is finally drying into firm soil. Freshly paved roads stretch out across ground that was ocean floor just 30 years ago. It is an undeniable, awe-inspiring testament to human will and engineering brilliance. But twice a day, every single day, the untamed Yellow Sea presses 6 vertical meters of heavy, crushing tide against the outer face of that rock armor. And it waits. Because this structure is not truly a wall against the sea, it is a lease on the sea. A lease 33.9 kilometers long, signed heavily in cold rock and wire gabions. A lease paid for in the deafening silence of 300,000 vanished birds. And it is a lease that is strictly renewable only by constant, flawless, eternal maintenance. Because if there is one thing this project taught us, it is that humans may build, but the sea never, ever forgets. If you found this story fascinating, make sure to hit that like button and subscribe for more deep dives into the mega projects that are quietly shaping our world. What do you think? Was the engineering triumph worth the ecological cost? Let me know down in the comments, and I'll see you in the next video.